If you remember when we discussed writing integrals in double integrals over planar regions, we noticed that sometimes one order is bad and another order is good, right? Some integrals were impossible in one order but doable in another order. Well, the same thing can happen for triple integrals. So if you think about trying to calculate this triple integral, the way it's written, the x integral is on the inside, so we need to do the x integral first. So we need an antiderivative of, we could slide the 4 and the over 2 and the over z squared, we could slide those outside the x integral. So really, to do the x integral, we need to know an antiderivative of cosine of x squared. But I've got some bad news for you. This isn't going to happen. Right? This is one of those non-elementary integrals. There is no formula we can write down for this antiderivative. So we can't do the integral in this order. So if we can't do the integral in this order, let's change the order to some other order. Maybe another order would be better. To do this, we're going to have to think carefully about what region these bounds are describing. So let's start from the outside. Right? These outside bounds are z bounds. So for our region that we're going to be integrating over, in the z direction, it's from 0 to 4. Okay. The next bounds are y bounds, and those are from 0 to 1. Now remember, in principle, these y bounds could depend on z, but in fact they don't this time, which is good for us. Okay. And then the next bounds inside are the x bounds, and those are from 2y up to 2. Okay. So our x bounds do depend on earlier variables, on y in particular, so we're going to have to somehow figure out what region this is describing. All right, so in general, it's actually can be very tricky to turn a set of inequalities like this into a 3D picture of what's going on. Fortunately, in many cases, you can think about sort of the different perspectives on the shape that you get just by looking at 2 coordinates at a time. So let's look at the YZ perspective. Okay, so in the y direction, it's going from 0 to 1. In the z direction, it's going from 0 to 4. So in the YZ point of view on this shape is it's just a rectangle. Okay, now let's look at the yx point of view. This is the most important one for this example because our x bounds depend on y, and so we need y and x in the same picture. So let's look at our xy view. So we need to look at x equals 2y up to x equals 2, because those are the extreme values for our x's. Okay, so x equals 2, we can draw that pretty easily. That's this vertical line here. But x equals 2y, we're not used to thinking of y lines that way. We're used to having our lines solved for y, so let's solve this for y. We get y equals 1/2 x. So that looks like this. Okay? And x is going from the line. So in the x direction, we're going from the line to x equals 2. So that means we're going from the line, from the diagonal line, to x equals 2, along the x direction. So our region is this lower triangle. Okay, so looking at it from in the xy direction, we get this triangle. Looking at it in the yz direction, we get this rectangle. That means, I guess, we have some kind of ramp, right? That's what's happening here. We have, let's see if I can draw it. Drawing these things can be difficult. So let's see. I'm having a mental block. Oh, okay, so here's the x-axis, here's the y-axis. In the xy plane, we've got this triangle, and then looking at it in the YZ direction, so looking at it from this end, we see a rectangle, so it's this rectangle like this. Okay. But every, because the x bounds don't depend on z, every slice in the slice at every height will look the same as the slice at height 0. So that means all of the slices look like this same triangle. Okay, so we get this prism, right? It's got a triangular cross section, and as you go upwards, it's always the same triangular cross section, right? This triangular cross section is the same at every height. Okay. So understanding this picture is going to make it easier for us to write down our bounds, right? So the original order was dz, dy, dx. That's a bad order because we can't do that antiderivative. Because our y shows up in this bound, probably, right, the x integral is impossible, but the x integral has y in its bounds. So maybe we should be interchanging the order of x and y. Maybe that's the thing to do. Okay, so let's leave our z integral on the outside. Okay, so we're slicing, that means we're slicing this region at constant z values. So I already have a picture of this cross section at height z, right? It looks like this triangle. And we have cross sections from height 0 up to, what was the upper bound for z? It was 4. Okay. Okay, next, let's put our x integral, and then we'll have our y integral on the inside. So along one of these slices, so remember all of the slices look like this triangle here. So for this slice, so if we want to do our x integral, that means we're going to be slicing this vertically now instead of horizontally. So what x values give us slices? Well, the furthest left slice is over here at x equals 0, and the furthest right slice is over here at x equals 2. Okay, and then for our y integral, along one of these slivers, what are the y values? Well, the lowest one is at the bottom, that's y equals 0. And the highest one is up at the top, which is this diagonal line, and that diagonal line is y equals 1/2 x, so 1/2 x. And then our integrand was, I should have left more room for our integrand, 4 cosine x squared. Oh, uh-oh. Got stuff showing up all over the place. Can I highlight this and move it? Okay, good. Okay, so it was 4 cosine x squared over something times root z, 2. Why do I have a 4 and a 2? That's silly. So 2 root z. Let's get rid of a factor of 2 here. Okay, so now that we have this order changed, can we do the inside integral? Well, yeah, the inside integral is with respect to y. There aren't any y's in this integrand, so doing the inside integral is going to be very easy. Let's move that 2 all the way to the outside. So 0 to 4. Our x integral is from 0 to 2, and then when we integrate with respect to y, we get cosine x squared over square root of z times y, and that's from 0 to 1/2 x. Okay, so now when we plug in these bounds, we get 2 times the integral from 0 to 4, integral from 0 to 2, cosine x squared over square root of z. Okay, now we need to plug in our bounds. 1/2 x minus 0. I left off my dx and my dz here. I need a dx and a dz. Okay. And now, well, now we can keep going. I guess for one thing, this 1/2 cancels that 2, so we don't need this 2 anymore. And our integrand is a product of a function of x and a function of z. And our bounds, now that we've taken care of that inside integral, our bounds are all constants. So now we can separate the integral. So integral from 0 to 4, 1 over square root of z dz times the integral from 0 to 2 x cosine x squared dx. And of course, having this x on the outside in our x integral makes all the difference, because now a u substitution will let us compute that integral. So let's see. For our z integral, this is going to be 2 square root z, I think. So if we take the derivative of that, a 1/2 pops out, and the square root moves down. Yeah, okay, from 0 to 4 times. And then for this, we get 1/2 sine x squared. Let's double check that. If we take the derivative of sine of x squared, we get cosine x squared, but then the chain rule spits out a 2, which cancels the half, and also an x, which produces that half. So that's right. And we're going to go from 0 to 2. So now we can evaluate everything. So 2 times square root of 4 is 2, square root of 0 is 0, times 1/2. That 1/2 cancels this 2. Sine of 4, whatever that is, minus sine of 0, which is 0. So we get 2 times sine of 4. Okay. So the upshot of all of this is that you aren't stuck with the order that you're presented with if somebody gives you a triple integral to evaluate. You can change the order just like you can for double integrals. Of course, the visualization task of understanding the region that we are integrating over is much more difficult in triple integrals than it is for double integrals, because it's just harder to visualize 3D things. Okay, but if you can visualize the region that you're integrating over, then you can switch to a more convenient order.